Hi, this is Tariq Rashid. This is another class of backpropagation algorithm, part 2, which is a practical example for a simple neural network um, on backpropagation algorithm. Backpropagation algorithm, I believe it's a magic. If there is magic in our life, then I will consider backpropagation is magic, and it's a beautiful learning algorithm. Now, key mathematical rules in backpropagation algorithm: delta equals partial differential equation of partial derivative of error over partial derivative of output, then partial derivative of output over partial derivative of net. So if we can say that this goes with this one, then we will get that term, that we get this term, okay? And that term equals this one, and we come to it how we can find this one. Now, for the derivative of hidden layer, it will be sigma of derivative in the output layer, multiplied by their connection weights, multiplied by delta E, or delta E in relation to hidden layer. So that's in relation to the hidden layer. And for the weight gradients for the input layer to the hidden layer, that is delta E over delta W, the derivative multiplied by input. Now, to update the weights, which will be the new weights, old weights, minus the learning rate, which is the parameter between 0 and 1, and then delta E over delta W. For the bias connections, again, bias, old bias, minus learning rate multiplied by delta. So that's the basic calculation, and we come to this problem. If we have a problem of two neurons, two hiddens, and two outputs. So and there are biases to each one of them. So that is the network that we are trying to make sure that we implement learning algorithm on this network. Now, the inputs are this one. So the inputs are these are the parameters of the network, if we can try. So that's I equals two inputs, 0.05 and 0.1, I1 and I2. Hidden net connections to the input to the hidden connection, weight 1, these are the values are given. Hidden to output, these are the values are given. And the biases are B1 0.35 and B2 is 0.6. It's a supervised learning, therefore we need targets. Target 1 is for the neuron 1, 0.01, and for neuron 2, 0.99. Now, sigmoid functions are used at both layers, so squashing the net so that we can get a better output from each neuron, and the learning rate we assume it as 0.5. Now, feed forward in the hidden layers. So sigma of inputs multiplied by their connection weight. So I1 multiplied by W1. So I'll go to, so I1 multiplied by W1 for this network, to show you, to find the net of this neuron. So I multiply by its weight connection and I2 multiply by its weight connection, and we find this one. For this one, I multiply by this and I2 multiply by this weight connection, we'll find this one. Likewise, so we apply sigmoid function. So we'll get out here and out here. So the out multiply by this one and out multiply by this one, we'll get this one. And out multiply, this out multiply by this one, and out multiply by this one, we will get this one. Now, once we get this one, it has target 1. This one, it has target 2. We will get the errors. Once we get the error, then we backpropagate to through layers backward. So here is the net as I explained earlier. So that's the net H. I multiply by W plus I2 multiply by W plus B. And then that's the result, and we will get the output. We put it, we subject it to activation function, sigmoid, we will get this result. Net for the hidden two, same thing, I1, W3, I2, W4 plus B1. Then we will get this result. Yeah, then we get that's just let me check. Okay, I2, B1, correct? That's correct. So we finish with the first layer, and this was squashed. That's the result. That's the result for two neurons. Now for output layer, same thing. It will be the net output of hidden one multiplied by its weight, and output of hidden two multiplied by its weight, and plus B. Then we will get output for B2, the bias 2. Same thing, this one and this one multiplied by plus B2 will get this one. Now we have two output at the output layers, and we have two outputs at the hidden layers. We found them. We will try to find the error. The error is 1/2. We said 1/2 is mathematical convenience to reduce the error to a better rate or to minimum. So target 1 minus out, target we have it, and minus out that we found it. That's the error at the first neuron. And error at the second neuron, target 2 minus out, we'll find target at the. Now, E total, this one plus this one, that's E total we found. So out one, E1 plus E2, it's E total. E total. Now we do backpropagation. Now this is very important, the backpropagation. Here the backpropagation is done in this way. We have, that is the output neuron. Okay, so the error found, that error delta E over delta out, and delta out over delta net, and delta net over delta over W5. So that is the, if we have delta total over delta, that's one way, this figure same that I talked. So that's the delta E over delta out 1, and then delta out over delta net, and delta net over delta over W5. So that's how we found the error in the output layer. So if goes this one goes with this one goes with this one, we'll have this that terminology with this one. So here we will find the change of the weight. Now we need to find this term and this term and this term, and we multiply them. Next, we will do the calculation for this term. So derivative of error with regards to output, we will have this one. Here, derivative of this one, it will be 2 multiplied by half, multiplied by t minus out, multiplied by, for the output, the derivative of output, it will be only -1. So -1 multiplied by t1 minus out. So that's the result. We found it. And the sign will multiply to enter, it will be x minus t. X is the out. X is the out one in general. Now that we found it, the first term, and we put the values of T1 and out 1, we'll find the value of delta E over delta out 1. Now we need to find the second term, which was called derivative of sigmoid function. So delta out over delta net. Delta out over delta net, it is the derivative of this one. The derivative of this one, it'll be, we need to drive this one. And driving this one will be easy. We'll say, for example, if we have fxy, y equals the sigmoid function 1 over 1 plus e minus x. That's sigmoid function, by the way, this sigmoid function. So that is the sigmoid function. So the net will be here inside the sigmoid function to squash the net. So here we have this part, sorry, we have this part multiplied by derivative of 1, 0, minus 1 multiplied by derivative of this one. It will be only minus ex to the power x. And then it will be e minus x over 1 plus e minus x over 2. So that's the result of, because that minus will multiply to here. It will be e minus x over 1 plus e minus x squared. Now, if we assume that 1 minus y equals 1 minus, the y is sigmoid function, which is 1 minus 1 over 1 over 1 over 1 plus e minus x. So that's 1 minus x equals, that's the 1, and y is this part. So we can multiply this denominator by 1, and we can also multiply this denominator by 1. It's 1. So you will get this result. Now, simplifying this one, it will be 1 will go with 1. It will be e minus x, 1 plus e minus x. Now, we know that in the earlier slide, we found that derivative of y is e minus x, 1 over e minus x squared. So I simplify this one. I make it 1 plus e minus x, I separate them and multiply by 1. So this part is the y, okay? And this part is 1, this part is this. This part equals 1 minus y, okay? And this part is y. So then 1 minus y times y. That's the result of derivative sigmoid function. Okay. Now, likewise, this simplification of it and delta out over delta net. That one wasn't the output for it, and so numerical substitution, we put them. That is the out, and that's 1 minus out. We will get this term as well. So this term is found. Okay. Now the last term, which is delta net over delta W. Delta net over delta W, we need to find out partial derivative of net out 1 over delta W. So here, that's out 1, and that's weight connection 5. So we'll have to find net. Net in the pass feed forward pass, it was W5 multiplied by output 1 plus output 6 multiplied by output 2 plus B. If I go back to that was that's the example that I have. That is the net out. Okay, that's net out. So derivative of this one, this part will be 0 because I'm doing out net. I do it according to the out. Okay, so out 1, out hit 1. So I'll show you here. So derivative of this one, it'll be this one 0, that one 0. It'll be only uh, out H, sorry, out H. So delta W5, for example, and that's delta W5. So it'll be only out. So derivative of this one is 1 multiplied by out, so you will get only this one. So that's the result. Likewise, we'll do for 6 as well, same example, and we do it for the B2. B2, derivative of B2 is 0, nothing there. So now delta net over delta 5 is only out because that's how we calculate it. If you do delta net over delta W, 5. So for 5, this whole term will be 0. This whole term will be 0, only this term. So in relation to derivative to W5, that's only 1. This would be 1. 1 multiplied by out H. So you get out H. Now, now we'll have 3 terms. We put them all together. This term, the first one, that term, the second, this is delta out over delta net, this delta net over delta delta E over delta out over delta net, and delta net over delta W. So we found it, that's the for W, which found the change delta E over delta 5. We can do the same thing for out 2, and out 2 we found it this much. So I mean, we consider this one is uh, uh, delta out 1, and that's delta out 2. Similar wise, similar we go for the second one. Now we come to the hidden layer. Hidden layer, it's here. We have 2 neurons, and that's hidden layer. That's weight 5, and that's weight 1. That's weight 1. So that is weight 1. So in this scenario, we will have this delta 2, and we have this delta as well for neuron 1 and neuron 2 for the output. So multiply by their weights, that's sigma, and then delta out over delta net and delta net over delta W. So delta out over delta net and delta net. So this part, it will be a sigma of it. Okay, sigma of it. Therefore, if we need a sigma of, we need to get the total error. And total error we found at the beginning in here. Error at the first neuron and error at the second neuron, sum them, and then delta E over delta net we find for the first one, we find for the second one, then the sum of them. If we apply the chain rule, it will be in this way, very simple. For the first one here, and for the second one is there, and we sum them up. Now, here is the delta out of the delta net, we found it. Here, delta E of second neuron over delta out second is this one. And delta out over delta net, we said that y multiplied by 1 minus y, that's also found. And now delta out over delta net is this one, okay, can be found. And then delta O over delta out H1 is W5, we know this one, and delta net and delta out net, delta net O neuron 2 over delta out H1 is 0.5, which is W7. So this is what I'm trying to say here. If you look at this diagram, so the delta here and the delta here, each one of them by their weight. So this by weight 5, and this is by weight 6. Okay, and then we have to find delta out over delta net, and delta net over delta W1. Okay, so here we have to find delta E over delta H out. Here, we need to find this one. We did this one. That is sigma delta multiplied by W. That's this part. So that's 1 to 2. It goes to K output, or K equals 1 to 2 neurons we have. Now the first term is found. We come to the second term. Second term, delta out at hidden layer 1. It will be out of hidden 1 multiplied by 1 minus out of hidden 1. So that is the second term is found. And we have to find the last term, which is net H, okay? Delta net over delta W, first connection. So this one, that's input layer, that's weight 1, output layer weight 5. So here we need to find the change of the error over change over delta W, but then this part we need to find a delta net over. So what's delta net? If we go back to password, net equals W1, that W1 multiplied by I, it's I, the input, plus W2 multiplied by I2, I2, I1. I1 multiplied by W1, I2 multiplied by plus B1. If I take you back to earlier forward pass, that's earlier pass, that's that equation. I'm talking about this equation. So we go back to here. Now, net derivative of this one in relation to W, so this part W2 will be 0, and B1 also 0. So delta net partial differential over partial differential of W1, it will be the derivative of W is 1 multiplied by I, you will get only I, so 0.5. Likewise, we will get I mean, if we multiply, this is term 3 we finished. So we did term 1, we did term 2, we did term 3, which is this one. So multiply all these terms now. And that is the results of delta E over delta W. Now we can do similar for we can do that's the final results. Of course, these are part by part is done. So that's the final results here. Now we have to do it for W2 as well. W2 similar way will be found. And if we did W2, then we have to go back to output layer as we did this one and this one and this one. That's the results of the first layer, second layer, output layer, hidden to output, the weight connection, the change of error in relation to the weights. And here for the hidden layer or input to the hidden layer, we have 4 weights, and that's their change. That's the change of W1, change of W2, change of W3, 5. And then we will update them. The old one, the old weight, minus the learning rate, that's 0.5, multiplied by the change delta E over delta W1. That's we found it. So that is the new weight. These are new weights. This is new weight. That's new weight for 6, new weight for 7, weight for 8. And we will do for B as well, the old bias minus the learning rate, same thing, multiply by the change that we have. And we will work out with all, we will update all the weight connection with the bias, and we will go for the iteration 2. Iteration 2, we will apply again forward pass and get the error and get the error derivative delta back to all layers, subsequent layers. If you have anything, that's my side. You can email me. Thank you very much for listening and watching this video.